Okay, let's talk about what pH is then. Yes? H3PO4 is phosphoric acid. Phosphoric acid. PHOS, PHORIC. Uh-huh. All right, what is pH? pH is a way of measuring the hydrogen ion the hydrogen ion molar concentration. Darrell, what did I say about sitting straight forward today? Sit up and look forward and keep it there.
There's nothing there, Mr. Phil.
I don't care. All right. Now, by definition, I said I was going to define a strong acid for you. By definition, an acid is strong if it dissociates. There is none. If it dissociates completely.
Unassociated.
Well, why don't you write it down? Let me define it for you. You got everything written down I just said?
If it dissociates.
Completely.
Need a synonym for that.
I've got a better way of defining it for you, but if you write it down first, then I can define it and we'll get through it. Okay, does everybody know what it means to associate?
To talk? Like
belong with.
Congregate.
Dissociate is the opposite.
If it doesn't belong?
So, and that's strong if it doesn't belong?
No, it dissociates. It breaks up completely.
If it doesn't break up completely?
It would be weak if it doesn't break up completely. It's strong because it does break up completely.
He use an example.
Yeah, I'm going to do that. All right, but this is a word you're going to need to know because it's going to come back and we're going to have it again in a minute. Okay? What that means is that if I have an acid that is strong, so just pick one of those 7 strong acids. I'm going to choose hydrobromic acid. Okay? Hydrobromic acid, if I put it in water, it dissociates completely. All of the hydrogen ions break away from all the bromine ions, bromide ions. Okay? So I get all hydrogens and all bromides. I don't have any of the HBr left over. Okay? So that's what a strong acid does. It completely does this. Not just part of the way, completely. By contrast, a weak acid like hydrofluoric acid, if you put it in water, some of it breaks up, but not all of it breaks up. Okay? So you really have the reaction going in both ways at the same time. It's called a dynamic equilibrium when that happens. We talked about dynamic equilibriums when we're talking about solubility. Okay? So a strong acid dissociates completely.
What's the arrow there for?
Because the reaction goes both ways. This reaction only goes in this direction. This reaction goes in this direction, and this goes in this direction. like the difference between a one-way street and a two-way street. Yes? Mm-hmm. All right. So we said pH is a way of measuring the molar concentration of this stuff right here. Okay? I need to give you one little shorthand for molar concentration. Because when we're talking about acids and bases in particular, and in some other things too, rather than write out molar concentration of the hydrogen ion, over and over and over again, chemists have come up with this shorthand. Okay? Anytime you put a chemical formula in a bracket, anytime you put a chemical formula in a bracket, it means the molar concentration of whatever it is that's in that bracket. Okay? In a bracket. It means molar concentration of whatever is in that bracket. Now remember, molar concentration is that capital M with a line under it. And it means moles of solutes over liters of solution. And if I don't tell you what the solution is, it has to be water.
You said anytime you put a chemical formula in the bracket, it means what?
The molar concentration of whatever is in that bracket. All right. pH then is a way of measuring this. Now you can measure it directly, but those numbers get really, really small.
What's between hydrogen concentration?
What now?
That little marking.
This right here?
No, between hydrogen and concentration.
All right, I scribbled something out. Okay.
Wait, what is that? So you say pH is a way of measuring what?
pH is a way of measuring this thing right here. Molar concentration of the hydrogen ion. Okay. Now we could measure it directly, but when you measure it directly, the numbers get really, really small. For example, in pure water, the molar concentration of hydrogen ions that's really, really small. So rather than do that, chemists have come up with something called pH. And pH means, by definition, the negative logarithm. The negative logarithm of that hydrogen ion concentration. Can you write this number in scientific notation? How would you do that? You would have a negative exponent. What negative exponent would you put on there? Yeah, you're going to move the decimal place 1, 2, 3, 4, 5, 6, 7 places. The decimal has to be between the first and second significant digit. Okay? So this number in scientific notation is 1.0 times 10 to the, since I moved to the right, it's a negative 7. molar. Okay? All right, let's practice logarithmic calculations then. You need to get out your calculator and find your LOG button. Can you do what? You got $1? Put $1 in the box over there. Just make sure you pick it up before you leave. You don't have to use it. You don't have to use it. All scientific calculators have LOG on it. Just put the box right here, right there. All right. Now listen. This is where it's going to get a little tricky, and you have to pay attention and listen. Some calculators let you put in this calculation just about the way it reads. And some calculators require you to back into the calculation. Okay? So I'm going to first give you instructions on how to put it in the way it reads. And if a calculator doesn't give you the correct answer, then I will show you how to back into the calculation. Okay? All right. So I need the negative logarithm. Well, negative doesn't mean this button. This is the subtraction button. On my calculator, negative means the change of sign button. Your calculator may have a different symbol for change of sign. Sometimes it has plus, slash, negative. Okay? Sometimes it has other things, but you don't press the subtraction button. You press the change of sign button. So change of sign, then the LOG button, and then I'm going to put in the number we're looking for right here. Now, since I have an exponential number here, okay, a scientific notation number, I'm going to use parentheses to put that number in there. 1.0 e negative 7. All right. Then when I hit enter, I find a pH of 7.
Your E is 7, right?
My E is 7?
What? Your E holding you just out of luck.
Your E stands for times 10 to some power.
So if you don't have it, you wouldn't.
I'll bet you have an E.
Your calculator's on the
All right.
Is it like EXP or ED?
EXP is the same thing as my double E button. All right. Now listen. What did I say if you didn't get the right answer? What we're going to have to do? Back into it. So if you're using one of these calculators, you got to back into it. Okay? So what we're going to have to do for this answer here is we're going to put in, quiet please, we're going to put in the scientific notation number first, this number. So 1.0 EXP is the same as the double E button on my other calculator. Change of sign is here, 7's there, equals. Now I'm not done yet because I haven't taken the logarithm yet. I have to put in this number first, and then after I put in that number, I'm going to hit logarithm. LOG is right here on this calculator. And now I'm going to change the sign down here. And there's the pH of 7 we talked about a moment ago. Okay? So that's backing into the calculation. Well, that's what I call it anyway. You have to understand the syntax for your calculator, and that's why you need a calculator of your own, because if you use mine, and you won't be able to practice at home, and the one you're using at home might not be the same one, might not do it the same way. So you have to practice with your calculator to be able to do these calculations. You need your own calculator. Okay? All right. So the pH then for this number is 7. And that's for pure water. Well, what would you expect the pH for pure water to be?
That's pretty neutral.
It is absolutely neutral. Now, what about rounding off? Here's the thing to remember. There is a separate set of rules for rounding off for exponents. We're not going to learn a new rounding rule. We're going to use the same rule as multiplication and division. Okay? Since I have 2 digits here, this answer is going to have 2 digits as well. Okay? I'm not going to make you learn a new rule, but I do expect you to learn, I expect you to use the rules I've already taught you. And we're going to apply multiplication and division rules for exponents and logarithms.
So you're always going to give us the molar concentration or we'll find the molar concentration?
pH is the molar concentration of the hydrogen ion.
I know, I'm saying like, before we go solving it and stuff like, to get the pH, you'll give us, like, you gave us what water was.
Yes. I have to give you something to calculate it from, sure. Okay? All right. Now let's go back and look at, remember what we're talking about, completely dissociating an acid. A strong acid completely dissociates. If you have a 0.010 molar, this is a practice problem, HI solution, what is the pH? We're going to put all these things together now to get the pH. Since HI is one of the strong, it's called a monoprotic acid, it has 1 hydrogen. It's going to dissociate completely. So HI, I don't even know what physical state it is when it's pure. Let's say it's a gas. Put it in water, it dissociates completely. Okay. Whatever the concentration of the acid is, if I have a strong monoprotic acid, the concentration of the hydrogen ion is going to be the same. If I have a strong monoprotic acid, the concentration of the acid and the hydrogen ion is always the same. And here's why. Molarity, molar concentration, is moles of solute over liters of solution. Moles is a counting number. The counting number is Avogadro's number, 6.02 times 10 to the 23rd. So if I have 0.010 moles of HI particles in a liter of solution, because that's what molarity is, and if I get 1 hydrogen ion from every one of these, then I want to have 0.010 moles of H plus in a liter of solution. So therefore, whatever the concentration of a strong monoprotic acid, that's the concentration of H plus. Okay? I'll come back in a minute and talk about monoprotic and diprotic and so forth. But if the concentration is this, if the hydrogen ion concentration is the same as the acid, and the acid is this, then this is going to be 0.010 molar. And pH, then, is the negative logarithm of that.
Don't you do that?
What?
Don't you change it like and make it with exponents?
We don't really have to here. We could. I could have plugged that big old long number in there. Okay, both of them are the same thing. This number is the same as that one. I could make it an exponent number, but I don't have to. But by making it an exponent number, I can figure it out in my head without having to use a calculator. All right, anyway, let's do the math here. Negative log, then, of this concentration, 0.010. So find the pH, then, of this solution. Put it in your calculator and find the pH.
How do you find the bottom of the molar concentration?
Well, if I give you the concentration, you don't have to find it. It's assumed to be that much in a liter.
And the molar value.
All right, everybody put it in, get a number, see the number I got? All right, good. So you're on track. That's great. Did you calculate it like I asked you to? Just put the number in. You don't have to put an exponent in necessarily. Just put in negative log of that number. That's it. Did you get the same number? Okay. Now, let's talk about my definition a minute ago. Monoprotic. 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 It means an acid with only one hydrogen that will break away or dissociate. An acid with only one hydrogen that dissociates. An acid with only one hydrogen that dissociates. HI has one hydrogen that dissociates. HBr has one hydrogen that dissociates. HCl has one hydrogen that dissociates. HNO3 has one hydrogen that dissociates. Those are all monoprotic acids. Monoprotons. One proton. Okay? When hydrogens leave an acid, they leave behind their electron, and all they're made of is a proton. Monoprotic. This acid has two hydrogens that will dissociate. So it's not monoprotic, it's diprotic. Okay? These are both monoprotic. So that's what monoprotic means. There's monoprotic, diprotic, triprotic, and polyprotic. Okay? One ionizable hydrogen, 2, 3, and some number more than one. Okay? Now, we're going to limit ourselves to dealing with monoprotic acids in the remaining time we have in this quarter.
Did you give us the definition of iodine?
I hope you can figure them out from this. If this is monoprotic, what does diprotic mean? Two ionizable hydrogens. Triprotic, three ionizable hydrogens. Polyprotic, well, more than one. We don't know how many it is. This is more than one. It's two or more. Okay? All right. If we can calculate the pH, then we can calculate some other things. So now we're going to go forward and we're going to learn how to calculate, well, we've learned to calculate the pH from the hydrogen ion concentration. We've got this and got the pH. Okay, now we're going to learn to calculate the hydroxide ion concentration and something called pOH. Small letter P, capital O, capital H. But before we do that, I want to refer you to the handout I just gave you a little while ago at the beginning of class. And look for page 26 in Unit 9. Page 26, I think it is, in Unit 9. Looks like that. Page 26 in Unit 9. Before we go too far, there's one little typo down here. It's not little, it's actually a pretty big thing. This should be not pH, but pOH. Make sure you change that. pOH down here in the lower right-hand corner. No place else, just the lower right-hand corner. 26. Now this graphic here basically shows you how to make all those other calculations. And we've already done this one right here. We started with the hydrogen ion concentration and found the pH a minute ago. And it tells you what to do to get there. Alright? Turns out there's a way to undo that. So that if I have a pH, I can also, from that pH, find the hydrogen ion concentration. Okay? So, a logarithm, let me define logarithm first. Logarithms are, well, let me spell the whole word out. I think that's right. Logarithm. Exponents on a base of 10. So just for kicks, to illustrate that, let's find a logarithm of 10. Find the logarithm of 10. In your calculator, find the logarithm of 10. Got 1? Well, an exponent of 1 just makes it the same number. That's where we're going to get our answer from. Let's do the logarithm of 100, which is 10 squared. Did you get 2? That's where our answer is. It's a logarithm is an exponent on the base of 10. Try 10 to the 5th. Logarithm 10 to the 5th power. Well, you may have to put 10 to the 5th power first and then hit logarithm. Remember, on that calculator you have to back into it. Say what? There's the exponent button right there, EXP. So if I'm using this little calculator, turn it on, 10 exponent 5 equals, whoops, I guess I didn't hit 5, let's try it again. 10 exponent 5 equals, and then logarithm. Whoa, that's not right. Alright, 10. Oh, I'm sorry. No. You're going to say 1 exponent 5 because that's 1 times 10 to the exponent of 5. Okay? There is an up caret on here, I think, somewhere. There it is. That's the up caret on this one, but that's okay. 1 exponent. Okay, and then you can hit the logarithm and you'll get 5. Okay? Again, that's part of knowing how your calculator talks, and I'd kind of forgotten about that one. Alright, so an exponent on 10 is what a logarithm is. Okay? Therefore, I can undo one of those by putting the number on a base of 10. So what that means is if I have a pH that equals 3, I can find the hydrogen ion concentration by putting that on a base of 10 as an exponent. But remember, pH 3 is the negative logarithm. Remember that? So therefore, the logarithm on the base of 10 has to be a negative 3. So the hydrogen ion concentration is going to be 10 exponent negative 3. Enter. And that's the hydrogen ion concentration. And that's what it tells you right here.